Hello, I'm Bo Weidema. This is the 9th video in a series of 10 on consequential modeling in lifecycle inventory analysis. The topic of this video is the co-product algorithm. This basically involves a stepwise procedure for substitution. The first step is to identify whether we have to deal with combined or joint production. So if the co-products can be independently varied, we have combined production, and the unit processes can simply be subdivided according to physical causalities. We will not deal with that any further in this video. For joint production, the first step is to identify what is the determining product. That is the issue that we dealt with in the previous video in this series. Now the third step is to identify whether the dependent product is fully utilized. If it's fully utilized, we have one procedure. If it's not fully utilized, we have another. So let's take them in turn. In the situation where the dependent co-product is fully utilized, substitution works in this way. First, we have the determining product. In this case, example, milk from a dairy cow. With this milk production, there will be a dependent byproduct, the meat output. Now that will then substitute another process, which is beef cattle, that produces the same amount of meat. So as you can see, this system has an output of a kilogram of milk and no output of meat. And that is exactly what we are asking for in this case. The process I, the intermediate process, could also be called the recycling process because it deals with the treatment that is necessary for the dependent byproduct to be able to substitute at the point of substitution. In this case, this could, for example, be the calf, raising of the calf to become a meat that is substitutable with the meat from the beef cattle. So what we can conclude here is that a demand for product A will cause the activities A plus the activity I minus the activity D, which is the displaced production. So there is no partitioning of any process, but just adding A plus I minus D. If we instead look at what happens if we ask for product B, that takes product D plus product B, because you cannot have any more output from products from the process A, simply because that is already fully utilized, which was the first condition that we were investigating. There is no waste in this situation. All the calves are raised to meat, and therefore you have the full substitution. And the only way you can get more meat out of the system is to ask for more of process D, because process A is already constrained by the demand for milk. There is a little additional thing you have to be aware of, and that is the situations where the B from process I is not exactly the same as the minus B from process D, so that the substitution is happening because they fulfill the same obligatory product properties on the market, but they may have different other properties. It could be a slight variation in content of different materials, and this difference in the composition of the two products B means that downstream in the life cycle of product B, there will be a slight change when you use the byproduct instead of using the output of the beef cattle. And that downstream difference in the life cycle of product B also have to be ascribed to product A, because that is causing the downstream effect. Vice versa, the downstream effect should not be assigned to the process D plus B, so the demand for more product B should not be affected by the difference if some of the inputs are modeled as coming from process A. So we're modeling the product B completely as a clean process from process D, process B, without any influence from the processes A and I stream input to product B. An example of this kind of substitution from ecoinvent. We have here the sheep production in this unallocated form. We have two different kinds of sheep, those that produce mainly meat and those that produce mainly wool. Of course, the sheep that produces meat also have some output of wool. And the sheep that produces wool also will have some output of meat. But these are still two very different kinds of production, one optimized for meat and one optimized for wool. We also have two markets on which we are selling the meat and the wool. The ecoinvent names for meat and wool are a bit more elaborate than we are using here. So how does this then link together in the consequential system model? First of all, we place all the byproducts on the input side with a negative sign. So we move the wool and the meat to the input side and give them a negative sign. A negative input is the same as a positive output. It signals that by having this additional byproduct, we're actually reducing the need, the demand for wool and meat. Then we link the output of meat to the meat market and the output of the wool to the wool market. This is straightforward. Then the input of meat, the negative input of meat to the sheep production, that is also linked as an output to the meat from the meat market, just as if it was a positive flow of input of meat. Essentially what we're doing here is that we're saying we have a reduction in demand for meat, and that reduction in demand is placed on the market, just like a positive demand would have been placed on the market. The same happens for the wool. The byproduct of wool from the sheep production for meat is placed as a negative demand on the market for wool. We now have a completely closed system that can be calculated with as a system of linear equations, and we can get the result for an additional output of meat or wool from the two markets. The second situation is when the dependent coproduct is not fully utilized. In that case, an additional amount of demand from product A will produce an additional amount of output that goes to waste. So even though some of that output may be processed into a byproduct that can be used in the product B, since it's not fully utilized, an extra amount will be going to the process W, the waste treatment. But if we're asking for product B, we would ask for more of process I as well, but since we cannot get more from there is no need for getting more out from the process A, so we're not stimulating process A to produce anything more. Instead, we're simply taking and avoiding some waste treatment that would otherwise have happened. So, in the case of non-full utilization, the demand for product A will cause the process A and the process W the waste treatment of the additional amount of byproduct. This byproduct could also be called a near waste because it's sometimes a waste and sometimes a byproduct. The additional amount is a waste. Now, if we instead look at the situation where we ask for B, then that causes process I and B and a minus process W, because we're displacing basically the need for waste treatment by using this byproduct, which is not already fully utilized. You could also say that the marginal supplying process is the waste treatment process. So what we're displacing is actually the waste treatment process. So this fairly simple coproduct algorithm has been shown as being the only algorithm that consistently maintains mass, elementary, energy, and monetary balances of the resulting single product systems. This is mainly because there is no partitioning involved in any of the activities. In Su et al. From 2010, the simplicity of the algorithm is clarified. Byproduct outputs are simply modeled as negative inputs. It's a simple mathematical operation. What is substituted by B is the input to the market that the negative input is linking to. So we already know when we're asking for more of B, what is the output from that market. So just having that with a negative sign, it is the same processes that are affected. So the justification of what is substituted is already given by the comparability and linking algorithms for the positive supply. The terms substitution and system expansions are sometimes used as synonyms. We can say that what happens in substitution is basically that we have an output of a byproduct that is sometimes treated, if necessary, and then it feeds in somewhere in another process where it displaces an alternative production route. The term system expansion somehow implies that your original system was incomplete. So if you're working with a complete database that contains all kinds of products linked together in a total global system, then the term substitution may be more fitting, because you're not really expanding your system, you're simply making a negative demand on one of the activities in your already existing systems. In practice, the terms are used as synonyms, as you can, for example, see in the ISO 14044 Annex D2 of the new 2020 amendment. Previously, this information was found in a separate standard called ISO 14041. Now, in a system here with two outputs, one of them being a byproduct, we're linking to another input somewhere else in the system. Typically, this will be somewhere upstream of our functional unit. And that means that everything upstream of that point will be slightly reduced. That may happen several times during our product system upstream. And that means that sometimes we will have reductions of reductions. So we will have negative negatives, which essentially is the same as a positive. So upstream of this second round, we will have a positive impact. You can always use mass balance as a sanity check for your total system after all the expansions or substitutions have been done. When substituting, no activities are partitioned, and that means that the level of each activity is simply adjusted up or down to accommodate the output requirements. That means that mass balances of each activity and of the entire system are preserved. If you find a lacking balance somewhere, that points to an error in your modeling. The use of negative flows may sometimes give cause for concern. What do we really mean by a negative flow? Well, typically what we mean is just a reduction compared to the baseline. We have a reduction, which of course we signal with a negative sign. In the case of waste treatment, waste is typically an input to the activity. Physically, it's an input. But we can, you could say, put a minus sign on both sides of this activity, and the resulting activity would then have a minus W output. So we can say that an input can be modeled as a negative output. A minus W output is the same as an input to the waste treatment activity. You could also see the minus W as the determining product of the waste treatment. It's driving the waste treatment. Similarly, we can look at the output of a production activity that has a waste output. This waste can also be changed into a negative input by putting a minus sign on both sides of the equation here. So the resulting system will have a minus input to the production of waste and a minus W output of the waste treatment. So the flow between waste treatment and production is like a demand from the production activity for having treatment of this waste, having this waste reduced and taken away from the production and treated in the waste treatment. In this way, an output can thus be modeled as a negative input, and this combined modeling allows to maintain mass balances when modeling the physical and economic causality for materials for treatment. I will now explain an example of a concrete case that we had for the two companies DuPont and Arla on modeling what happens in a dairy when you ask for more butter. So the focus here is on the modeling of butter. The challenge is that we have a co-production of milk and butter, and when modeling the life cycle emissions related to butter, it's really crucial to determining how the dairy production reacts. Conceptually, there are 4 different ways that the system can react to a demand. If we assume that both the milk and butter are determining co-products, then the demand for €1 of butter will cause the dairy production to supply €1 of the determining products, milk and butter. In the second case, if milk is determining, we can have a substitution of high-fat cheese with low-fat cheese. So the butter becomes available because the fat is not used in the cheese production. In the third case, we also have milk as determining, but instead we have a reduction in the milk powder that is substituted by vegetable oil. And finally, the fourth option would be that butter is identified as determining. in that case, the demand for 1 kilogram of butter will cause the dairy to supply 1 kilogram of butter, but there will be a lot of additional milk. So what we did here was analyzing all 4 possible systems to see, you could regard it as a kind of sensitivity analysis or as an experiment to see what would actually happen and what would be realistic and what would be plausible. So let's take first option 1, that milk and butter are both determining. The demand from the milk, from the butter production would lead to an output of 2.6 kilograms of milk and 0.289 kilograms of butter. And these together will then provide the same revenue to the dairy as the $5.45 that 1 kilogram of butter is worth. So we don't get all the butter that we wanted, only 0.289 kilograms. So the rest of the 1 kilogram of butter must come from some other users of butter giving up their use of butter and supplying that reduction to the market so that we have it for our use, for our demand here. At the same time, the dairy will produce 2.6 kilogram of milk that nobody had been asking for. So that will affect the market for milk and displace something else on that market for the users of milk. So somebody else will have to drink more milk, basically, or use more milk for some other purpose. This can, in a way, be compared to a pure allocation that does not consider these issues of market clearance and adjustments in consumption. So the typical allocation or partitioning of the dairy for butter and milk would mean that our demand for 1 kilogram of butter would lead to an increase in raw milk of 2.89 kilograms that produces 0.289 kilograms of butter. So obviously, since in the raw milk we only have 450 grams of fat, it's like fat is coming out of the thin air here. And this is one of the criticisms of partitioning, that it doesn't reflect reality. So to reflect reality, you would have to take the full consumption adjustments and market clearance into account. Option 2, where the milk is determining. Here we have no effect on the dairy because we're simply saying that all the butter comes from a displacement of the alternative production route. Now this substitution actually happens on the market for cheese. Consumers are, with price signals, asked to prefer low-fat cheese to high-fat cheese. And in that way, we have a surplus of fat that can remain in the butter for the demand for butter. So this substitution is simply an adjustment that happens inside the dairy in the cheese production. Might be a different dairy from the one producing milk and butter. The third option is that milk is still determining, but the displacement is not with the cheese, but with the vegetable oil used in milk powder production. Again, this typically happens in a separate dairy type, a dairy installation that produces milk powder, and there it's possible to use part of the input to the milk powder production from vegetable oil. This is typically from palm oil on the margin, and that means that essentially additional demand for butter displaces a production, and therefore you will see a induced production of palm oil into the milk production, and thereby liberating the amount of butter fat needed for our demand. So asking for more butter leads to more production of palm oil. Finally, the option 4, that butter is determining. That would mean that the full 1 kilogram of butter would come out of the dairy, requiring an input of raw milk of 10 kilograms and an additional output of 9 kilograms of milk. This additional milk would of course have to be used by somebody, so there will be a significant increase in the supply of milk depending on the demand for butter. This is not likely to happen in practice, that the milk market would be so dependent on butter. So this was one of the things that our experts at Arla said, this doesn't really sound like a plausible model. So what was the outcome when asking the experts at the Arla dairy? They basically said that milk is the determining product. And what happens is that when more butter is demanded, the two types of substitution would coexist, so that 25% of the butter would come from substitution of the fat content in milk powder by vegetable oil, and 75% would result from the substitution of high-fat cheese with low-fat cheese. This is, of course, a specific situation in Denmark for the Arla dairy, and it could be a different percentage or different situations in other countries or at other times. So with this example, we've shown how you can work with this as scenarios if you are in doubt which one is the most correct modeling. Thank you for your attention.